So in the last video, we talked about relationships between variables. Now we're going to talk about that same sort of thing a little bit more formally by talking about functions. So we're going to introduce two conceptual models for understanding functions. They'll give us a little bit more concrete way of thinking about what functions are. We're going to apply those models to some examples, and then we're going to use that to define some terminology that is related to functions. So here is the first model for functions. This is probably one that you are very familiar with in your previous experience. It's called the input-output model. So a function could be thought of as a machine where you give the machine some inputs, and every input you give the machine, it gives you some sort of output. So every time you put in an appropriate input, in other words, an input that the machine will accept, the function looks at it, figures out what to do for an output, and then gives you an output. And there's some sort of consistency in how this input-output means. So what can happen is you can put in an input, it'll give you an output, and if you put in the exact same input as before, it will give you the exact same output. So you can never put the same input in twice and somehow get two different outputs. But you could put two different inputs and get two different outputs from those different inputs, but not from the same input. Here's a model that I kind of like because it's a little more human-like, and I call this the question-answer model. And in this case, our function is not a machine, but it is a human, it is a person, and this person answers your questions. So what you do is you ask an appropriate question to the person, and what I mean by appropriate question is a question that that person is equipped to answer. And then the function, the person, gives back an answer for every question that you have. And you have the same sort of consistency as we had for the input-output model. If you ask the exact same question twice, you should get the same answer. So it's not going to be the case that you ask a question and the person gives you one answer, and then you ask the exact same question again and they give you a different answer. You can be confident that every time you ask them a question, they will give you the same answer to that particular question. So in this case, the questions are like the inputs in the input-output model, and then the answers are like the outputs. And then the person is like the machine. So, and then the second item in each model, that consistency one, that guarantees that the functions are always going to be consistent in their outputs and answers when you give them a given input. It makes it so that you can rely upon them to give you reliable outputs and answers. So there are different ways that you can define a function, and I'll go through a few of those, and this is not exhaustive, but that's a few to give you an idea of how versatile it is, this concept of a function. So one is you can give a rule, and one way to give a rule is just a formula. So if x is a real number, we can say f of x equals x squared, and that gives you a formula for a function. And to sort of unravel what that means in terms of our models, the input or question, depending on what model you're looking at, that is x. X is the input to the function, x is the question that you're asking the function. And then the answer or output to that input question is f of x, which is x squared. So x is the input, f of x is the output. X is the question, f of x is the answer. So for instance, if your input is 3, then your output is going to be, well, 3 is the x here, so 3 squared gives us 9, so f of 3 is equal to 9, that's the output. Now if we're talking about what the function itself is f. We really have three things going on here, right? We have an input x, an output f of x, and then the function itself is f, and that is what the rule is. That is what is controlling how you go from an input to an output. And note that we did kind of make a big deal about what a suitable input is. We demanded that x, the input, is a real number for this particular function. We could have used, say, complex numbers if you want to go nuts, and it's perfectly okay to square a complex number. But for this particular function, they only accept real numbers. Now, I should note that when you're using a rule, it does not have to be computational. So here's an example of what a non-computational but rule-based function is. So we're going to find a function g in the following way. So x, the input, is going to be a person, and g of x is going to be the age of that x rounded down to the nearest whole number. So if I give myself as an example, I am 52 years old. Well, actually, if you want to be really technical about it, I am between 52 and 53 years old. But of course, when we give our age, we always round down. So if I round down my age to the nearest whole number, then that's going to be 52 years old. So G of Darren, that's me, is equal to 52. Darren is the input. 52, which is my age, rounded down to the nearest whole number, is the output. So in this case, this is not a formula, right? You don't take Darren, me, and do some kind of computation with me. And in fact, you can't, because I'm not a number, I'm a person. So some functions, we can just express it as a list of ordered pairs. So here's a function h just as a list of ordered pairs. So h is equal to, we got the curly brackets indicating that we have a set. We have 1, 5, 2, -1, 3, 7, and 4, 0. So how does this relate to inputs and outputs? Well, if you look at the x-coordinate, that's going to be the input. The y-coordinate, that's the output. So let's look at that first ordered pair, x equals 1, y equals 5. X is the input, so that's what you're going to put into the function, h of 1. 5 is the output, so h of 1 is equal to 5. If you look at the second ordered pair, the input is 2. The output is -1, so h of 2 is equal to -1. For the third one, we have h of 3 equals 7, because 3 is the input, 7 is the output. And finally, for the last one, the input is 4, the output is 0, so h of 4 is equal to 0. And as we did in the previous video, anytime you have a set of ordered pairs, you can also express that as a table. So we have the x's, the inputs on the top row, the outputs on the bottom row, and the inputs and outputs that correspond to one another are in the columns. So if the input is 1, you look for the output right below it, that's 5. If the input is 2, you look for the output right below it, that's -1. 3 is the input, the output right below is 7. 4 is the input, the output right below that is 0. Again, the same information as the set of ordered pairs, just expressed in a slightly different way. Alright, so now we're going to talk about the domain of a function, and the idea behind this is it is important to know what inputs are appropriate for a given function. If you just start throwing random inputs into a function, some of them the function might not accept. The function might see the input and say, I don't know what to do with this, I'm tossing it out. So it's important to know the domain so that you can give the function relevant inputs. So the domain of a function is the set of all possible inputs that you can put into that function. So for instance, when I said f of x equals x squared, where x is a real number, I am demanding that the inputs you give this function are real numbers. That's my x. So the domain here is the set of all real numbers. Now if g of x is the age of the person x, that where we round it down, well, let's see, the inputs are going to be, we're finding the ages of people, so the inputs are going to be people. That means the domain is the set of all people, right? We're saying x is a person, so if you look at the set of all people, those are appropriate inputs for that function. And then finally, if you look at the ordered pairs 1, 5, 2, -1, 3, 7, 4, 0, you can just look at the inputs from the x-coordinates, right? The first input is 1, the next is 2, the next is 3, the next is 4. So that means the domain is the set of the numbers 1, 2, 3, and 4. And just as it's important to know what kind of inputs you can get in, it's important to know what type of objects you can have as outputs. Now, we don't care exactly what the precise outputs are. We just want to know what kind of objects they are. So for instance, the definition is the codomain of a function is what type of object you get as an output for the function. And there can actually be more than one answer to this, right? For a domain that was very set in stone, these are the things that you can put into the function, these are the things you can't put into the function. But for a codomain, you can define that in actually legitimately more than one way, and I'll show you how in a little bit. So for instance, if we have f of x equals x squared, where x is a real number, I know the input is a real number, the output is what you get when you square a real number. Well, if x is a real number and if you square it, that's always going to be a real number, which means that if we wanted to, we could say the codomain is the set of real numbers. And all that really says is that no matter what my input is, my output will always be a real number. May not get every real number, but I know it'll be one of the real numbers. But you could also say, if you wanted to, that x squared is always non-negative. If I take a real number and square it, I can't get a negative number. So if I wanted to, I could say the codomain is the set of all non-negative real numbers. And again, what that means is no matter what my input is, my output will always be a non-negative real number. So both the set of real numbers and the set of non-negative real numbers are reasonable things that we can call the codomain of that function. We can actually choose between those. And let's see, so if g of x, that's the age of x rounded down to the nearest whole number, where x is a person, there's a couple of things that we can have for the output. So the outputs are going to be ages of people, right? So we can always just say, the output, that's just going to be a whole number. No matter what you put in, we're always rounding it down to the nearest whole number, so you're always going to get a whole number. So if we wanted to, we could define the domain as the set of all whole numbers. That's fine. But if we're confident that no one has ever lived past 130 years, we can say, look, a lot of those numbers we don't have to include. We don't have to include anybody beyond 130 years. So I can just say the codomain is the set of all whole numbers less than or equal to 130. Both of those are reasonable things that we can call the codomain, because no matter what input you have, it's going to be in one of those sets. And finally, if you have the function h that's defined as a set of ordered pairs, as shown, we can be lazy if we want. We can say, yeah, all the outputs are integers, fine. So the codomain is a set of integers. But if we want to be really precise about it and say, oh, but the only integers that you actually get are 5, -1, 7, and 0, you can just list those as as a set. So you can say -1, 0, 5, and 7. That's the codomain. Both of those reasonable codomains. Now, with the range, it's a little bit different than the codomain, because with the range, we want to know what the actual outputs are. Now, here we're being very precise. There's only one answer. We want the outputs that contain all the outputs and nothing that's not an output. So the range of the function is the set of the actual outputs of the function. So for instance, if I'm looking at f of x equals x squared, where x is a real number, we don't want to include all those negative numbers because we never get them, right? They're all going to be non-negative, and so the range is going to be the set of non-negative numbers. G of x is the age rounded down to the nearest whole number. We want to only get the actual ages of people. So, up in that upper range, there might be some people who aren't there. So I kind of checked to see currently what's going on. Right now, there's nobody who's 118, 120, and 121, as far as I could tell. So if we wanted the actual range of that function, we get all the whole numbers between 0 and 122. That's the oldest right now, except we're leaving out 118, 120, and 121. So if we wanted to get the actual outputs, be really super precise about it, that is what the range is. And finally, for the set of ordered pairs, we're just looking for the actual outputs. So there it's going to be -1, 0, 5, and 7. Those are just the 4 different outputs that you get from that function, the 4 different y coordinates. All right, so now I think you're ready to work on the activities for Introduction to Functions. That will be on the PDF file included with this video.